All right, let's look at another example here, uh, and this example is going to have some different kind of joints, meaning it's going to have some prismatic joints, meaning that its link offset can change or it can get longer. So let's sketch what that might look like here. Um, so what do you want to start with? Well, let's do this here. We've got our our grounded point, uh, where the robot sits on, and we've got these joints that can move up and down, kind of in a linear fashion, right? And so that is what our prismatic joint is, and have that, and got another prismatic joint. And we've got our end effector. And also, we've got something going on here. We're saying this joint can rotate 180. They almost kind of got like a crane thing here, right? Where we can rotate around this way, move up and down, we can move in that direction. So we've got cylindrical coordinates kind of going on here, but we're not going to dig into that at all. Um, so I guess our first thing to do is to start assigning some coordinates here. So we've really kind of got uh, a four really joints things that we want to look at. We've got this guy 0. Got what's going on here is 1. This guy's 2. This guy's 3. Uh, so let's go about actually assigning some coordinates here. So I'm gonna simplify my diagram a little bit here. Uh, so our base coordinate system, our base coordinate system is going to be kind of at the ground here, and we're gonna oops. And so we've got uh, we always want to assign our z in the toward the direction of motion. Either it's rotating around z, or for prismatic joints, z is pointing at the direction of the motion. So in this case, we want our z for our base to be pointing toward this motion, right? Because it's going to kind of extend up that way. Uh, Additionally, sorry, that's not entirely correct. What we really want is we want z to be facing up this way because the rotation at point 0 is around z. Sorry, that's the right way to do that. So that means our axes are going to be, find some convenient, a right hand rule. This is z0, y0, and x0. And then we've kind of got another coordinate system that's uh, embedded in this joint here. So what we're going to do is we're actually going to have it have the same exact orientation. And that's because the z should point in the direction of the motion, and since it's prismatic, the motion is this way. 1, y1, x1. And now we get to this kind of point, which is saying is also the prismatic part. And the motion of z is this way. Or sorry, the motion of this axis is kind of this way. So that means our z-axis would also be that way. So we're gonna kind of copy 1, except for we're going to rotate it just a bit. We're gonna rotate it on the x-axis such that the z is facing this way. The y will now be facing down. That means we've got this is our z-axis. Our x-axis is still kind of pointing out, and we've got our y. That means we've got z here, x here, y here. And finally, we've got our end effector. And our end effector, we're actually just going to mimic and have the same orientation as. That's just going to make things. So these should be 2, 2. This is this should be D3, Y3, X. So just kind of imagine these guys superimposed over that figure. And now what we can start doing is making our table here, looking at the 4 parameters for each joint. So we're going to look at links 1, 2, and 3, right? So 1, 2 are the really real active part. Well, sorry. So 0 is also active, and then it rotates. What we're going to look at is got our link. Here, let me actually close this in here a little bit. Space. We've got our link name. Find our R1, or sorry, our I. Alpha I, DI, and theta I. And we want to find that for links 1, 2, and 3. So first off, looking at 1, we want to remember our definitions here for basically how we distinguish this R1 from RI and DI, alpha and theta, how those are distinguished and how we know which one we're actually should be measuring, which one we should be using. And that's why the definitions that are given to you are very important. So in this case, it's going to turn out that Ri is going to be 0. Because our definition is the distance along xi from origin I to the intersection of xi and the zi minus 1. Let's take a second and break that down. So the distance along the xi, that's this guy, the distance along this xi, from oi, so here, to the intersection of the xi and zi minus 1 axes. The zi minus 1 is right here. So if we look at that, if we kind of scale that guy up, the distance along the xi is 0, meaning that there's no offset. This doesn't come out any further than the x-axis. So that means that Ri is 0. But we know we do have some sort of distance component here. And that distance component has to do with it has to do with the di. And the di is defined as the distance along the zi minus 1. So if we're looking at 1, I minus 1 is here. The distance along zi minus 1 from O minus 1, so this point right here, O minus 1, to the intersection of the xi and zi minus 1. So this is xi, and this is the zi minus 1. So it's basically saying the distance from here to here. That's what it's talking about. And so we're not really given that, right? This is kind of an abstract problem. So what we're going to do is we're just going to call that D1. Let's put that on our table here. D1. And we also need to know our alpha I. So our alpha I is the angle between the zi minus 1 and the zi. In which case, the angle, these guys are pointing in the same exact direction, so therefore there's no angle between them. So throw there. And last but not least, we've got our joint angle. And our joint angle, well, that's going to be something that's going to be determined by 0, right? So as 0 rotates, this angle is going to move as well. In which case, we're just going to say theta 1. So the joint angle is the angle between x I minus 1, so x I minus 1, and x, or this is x I minus 1, and xi measured about the z-axis. So as this rotates, right, this rotates around, the angle between this x-axis and this x-axis is going to change, and that angle is going to be theta 1. All right. Now, let's look at 2 here. So, what's happening with 2? Well, let's just kind of go by each value. So, Ri is, once again, our definition, the distance along xi from OI. So the distance from xi, so that's xi, distance along xi from OI to the intersection. So that's measuring the this, as you can see, this this gets very tough to kind of keep track of what you're looking at or what you're doing. So let's draw some stuff here to really keep track here. So we're looking at the distance along the xi. So this is the xi axis, right? This is xi. Or xi. The distance along the xi from the OI, this is, in our case, this is our OI, to the intersection of the xi, this axis, and the zi minus 1. That means if we extend the zi minus 1 upwards, it's the distance on this x-axis, in which case it's 0. We're going to put a 0 there. Now, we need to look at our alpha value now. So the alpha I is the angle between the zi minus 1, this is the zi minus 1 now, and the zi, this right here, measured about xi, okay, right here. And we actually see that if we were to project zi up here, have this line, and we'd have an angle here, and this angle is actually 90 degrees. And it's a negative angle, so I'm going to put negative 90. And the distance here, so this d1, we're saying is fixed, right? The length from here to here, this is fixed. But this guy is going to change. Okay, so this is a variable, d2. And so d2, and I'm going to put a star there indicating, put a star by all my variables. That's a variable as well. And so last up, we've got our theta value. So the angle between xi minus 1, we've got, this is our xi minus 1, and our xi. And so the angle, well, it turns out as this guy rotates, so will this guy. So that means that there's never going to be any angle between those. So that means, say those are 0. That's 0 there. And last but not least, we can look at number 3, which is this guy here. And Number 3, well, as it turns out, has an Ri of 0. All these have Ri's of zeros, and that's because the z-axes are on the same exact line. But eventually, you'll potentially kind of find some of these tricks and things to notice if you're using Ri or Di. And it turns out that alpha is also a 0. In fact, there's no angles between these guys, so alpha and theta both be 0. And then our Di minus 1, well, this is a varying distance here, right? And so we're just going to call that D3. That's also a variable. Phew! So there's our table, and I think I'm gonna split this into 2 videos just for the sake of not having a super long video.